Hello. I'm going to present today the work that we've done at our division, Robots, Perception and Learning, at KTH within the SMART project on estimating bathymetry from the sidescan sonar. And just like to say that, of course, this work that I'm presenting is work done by my students, Yuping, a PhD student who has been working for 2 years on this, or 3 years if you count his master's student's thesis, and Niels Bohr, who's a postdoc here. He's been with us since the beginning of SMART. And so we have problems with sidescan sonar. What is it that we're trying to do? Well, we're trying to invert essentially a model of the sidescan sonar. So if you imagine the sidescan sonar model takes a sort of a bathymetry or basically objects along the sea floor and turns them into a sonar image. We want to take that sonar image and recreate the sea floor essentially. So we want to invert that, and that inverted problem is, of course, a little ill-defined, as they say, because, as you probably know, the sidescan is giving us these ranges away from the vehicle, but it's this entire wedge that you get an intensity from. So, I mean, basically, you can imagine intensity at each of these arcs here. It's basically accumulated signal along this arc. Most of the arc is the water column, and there's not much reflection from it. And then this point along the bottom is the most of the reflection. And the problem is we don't know where along this arc the reflection came from. So we can't recreate the sea floor necessarily from one ping, for example. But we do have some idea of how the intensity will vary according to the angle in which it hits the sea floor. That's what we're going to try to exploit. I'll talk about that a little later. So that's a hard problem, or even an impossible problem if you don't think of some tricks. And so maybe it was easier for us in the beginning. We thought, well, let's try it from the other direction. So let's try to understand how the sonar image is created from a bathymetry image. So that would be sort of like a sonar simulator, if you will, as a simulation of the sonar. So I'm going to show how we started off looking at that. Of course, the signal you get from the seafloor doesn't just depend on the point here. It also depends on what that surface is made out of and the properties of the surface, which we also don't know. So that's also a problem. So why will we do this? I mean, so this is the slide where I'm sort of going to motivate my sort of vision on where we're heading. You know, in maybe by the end of this project we'll be there. Well, we won't be completely there, but I mean, we'll have the pieces in place, let's say. So, I mean, my vision is that we would sort of go out with a smaller boat with relatively small, inexpensive AUVs that have side scan, that have some sort of DVL on them so that they can navigate well enough. And maybe some other sort of navigation aids, but not this sort of really high-end navigation necessarily. But we'd have several of them, and we would just dump them off the side of the boat. You know, I'm imagining ones that you could actually throw in the water with your hands. I mean, and they would just go out and do a survey in some sort of multi-agent cooperative manner. And that would be optimal for what we're going to do later with the data. So I mean, what they do and how they move is going to be important, but that we haven't gotten into yet really. But it's clearly going to be important. And then you would collect the side scan data, and you'd make sure that when they're moving, that there's lots of overlap in that side scan data, because it's that overlapping regions that we're going to be able to exploit to get the bathymetry out. I'll explain that as we go through this. And then you would take all that data and post-process it, and you'd end up delivering a very high-quality product of bathymetry, which I think could be as good as what we're getting with the multibeam, the really high-end multibeam sonars that we have now. We have certainly seen that we can approach that already. So we're going to use neural networks, and what's the advantage of using a neural network? I mean, the difference. So you could just try to understand the physics of what's going on and try to build physical models, and we're also going to do that. But I mean, the neural networks have this advantage that you could sort of avoid having to make any kinds of assumptions about the physics, and you could just simply collect data and learn the seafloor. And of course, then your application area is going to have to be similar to your data that you have. But we've also seen that we can collect data, for example, in saltwater environments and at sea with one type of very sort of rocks and silt kind of bottom, and then go to another lake environment with a somewhat different bottom, and it still seems to work, even though it was trained in the one environment and the other. Of course, there's limitations there, but the idea is that the stuff that we can't model can be learned. Like I said, we can't really know what the seafloor is made out of, but maybe there are clues in the whole sonar image that would help it understand that this looks like rocks. This looks like rocks. This is probably going to reflect in a different way from this other region that looks like sand. I mean, looks like is hard for us to quantify, in any sort of program it in by hand, but the neural network will maybe be able to learn that. We'll see. So that's the idea. Is we'll have these are the three sort of tricks that we're going to apply. We're going to apply replacing physical models with neural networks in some places, or non-parametric models, if you will. I mean, it doesn't have to be a neural network. We're going to exploit the fact that we know some of the bathymetry, even if we have such a simple setup, because all the AUVs always have an idea of what their altitude is. I mean, they usually have several sensors telling them the altitude above the bottom, and we can use those altitude readings as sort of very, very sparse bathymetry readings. Those are going to be important later. I'll show you how. And we can also, of course, exploit consistency between multiple views of the same part of the seabed, and that we'll also exploit in order to do this. So these are sort of the three sort of things that we're going to combine together to try to do this. So what is limiting us? We're going to need to have data, of course. I mean, especially if we're going to use neural networks, we're going to have to train them, so we're going to have to get the right kind of data. So, and when we're doing this as well, we're going to need to have excellent navigation estimates. I mean, we're going to need to have those when we, for example, try to calculate what's going on in overlapping regions, because if we have the same region seen from two different views or two different AUVs even, we're going to have to understand their relative position to one another in order to make sense out of it. And then we'll also, if we're going to be training with sidescan and multibeam data, using multibeam to train the sidescan, then we'll have to register those that multibeam mesh very well to the sidescan, and that also requires probably a navigation estimate as well. That's good. So we'll see how much of that is not always important. But anyway, right here I'm going to just show quickly a very short video of how we did when we tried to simulate. So, okay, excuse the flashing on the screen. It seems to do that sometimes. I'm not sure why. But it's doing it more now than it did before. Okay, good. So here you see, it's hard to tell. I mean, basically, I'm just showing it. It's hard to tell which one of these two on the right there is simulated. It's the one to the left that is simulated, but it's actually really hard to tell. And this was done using a neural network. I'll go through very quickly how the neural network is set up now. I'm going to go through this simulation neural network. I'm not going to explain any other neural network training very detailed, but just so you get some kind of a feeling for how we train these things. So what we have here is we have over here we have the bathymetry that we have formed from our multibeam data. We need multibeam data, like I just said, in order to train the neural network. Afterwards, we're going to estimate. For this, we're going to go from bathymetry to sidescan. So, of course, we need the bathymetry is going to come in, and then we'll take that bathymetry, and we also have a sidescan image from the same region, and we'll need to have that registered, like I said, properly, so we could sort of understand that these are the same areas. And then we would sort of translate the bathymetry into what we're calling here an incidence window. But basically, this is a very poor sidescan simulation. I mean, this is a sidescan simulation which isn't taking account lots and lots of stuff. It's just doing the most simple kind of simulation of the sidescan that you can from geometry. And it's creating a kind of a fake sidescan image that anybody could recognize as fake. And then we have the real image down here. And then, so there's a couple of ways we could train this thing in the middle here, which is going to convert this image into the generated window, as you see there. This generated window being the fake side scan that we're trying to simulate here. Now, we could train this thing in the middle, which is a neural network, by just taking the real side scan of this area and saying, okay, pixel by pixel, what's the difference between these images? Getting an error essentially, and then feeding that error back through this network and training it that way. That's what I would call regressive learning, regression. But what we did here is actually what they call adversarial training. That's what the A is, adversarial training, and that's where you have this other piece here, which is basically a piece which is given all three of these images, where these two are sort of randomly shuffled so that it doesn't know which is which, and then you ask this so-called discriminator here which one of them is real and which one is fake. And if the discriminator gets that right, then that means the generator network did a bad job, because the discriminator was able to tell this was fake. You're supposed to make something you can't tell it's fake. So this one is trying to fool the discriminator, and if it doesn't manage to, then we feed it an error signal back and train it. And if the discriminator, on the other hand, gets fooled, then it gets trained to get to be a better discriminator. And so these two sort of fight against each other. And if you carefully set up the training weights and so forth, you can get this to converge and learn in a different kind of way. So here's some examples of the training images. So you see these sort of, like I said, these very poor kind of side scan here. You see almost anybody could tell this isn't a real side scan, and these are the real side scans. So that's sort of what goes input to these networks. And then here's some results that are a little interesting, which I'm going to show you now about the GAN network here. See, the GAN network is producing an image that doesn't really match the ground truth, but the interesting thing is that it has put these ripples in there where you see no ripples in the input to the neural network. The neural network had no idea there were these sand ripples there based on this, which was its input. But the network imagined these ripples because it's trying to fool that discriminator, and a discriminator could easily see if this was smooth. It would say, oh, wait a minute, that's not what the seafloor looks like. I know the seafloor has got ripples for some reason. I mean, the discriminator somehow figured out it was going to have ripples, and then it would be able to identify it. So it had to make up ripples, even where it couldn't actually know where the ripples were, in order to fool the discriminator. That's just sort of the way these adversarial networks work. So trying to get the bathymetry, now moving on to bathymetry from sidescan, which is really what this talk is about. That was sort of to give you a little warm up into how we use the neural networks. So now I'll look at the problem of taking a side scan like we have here on the left. It's a pretty dark looking side scan, but it's a side scan anyway, and then we have a bathymetry of the same area, and we're trying to sort of train a neural network to learn to generate this bathymetry when you input this side scan instead. So that's and in this case, that's why I mentioned regression and GAN training. I mean, there's the regression training and the adversarial network, because we're going to do both of those now. We're going to be able to see clearly how they differ from one another exactly. So just to get right to the point now, I don't have to show you the networks or anything, but I kind of explained a little bit the difference between a recursive, a regression estimate and a GAN network. I mean, the C stands for conditional GAN, but never mind. This is the GAN output. This is a regression output. So the regression output is going to try to take every pixel. These are the produced images from of the bathymetry from the neural network for this region. It had a side scan input, and it generated this one network, and the other one generated this on the other side. And here's the ground truth. So I have to mention that these brown spots, what are they? Well, you know that in side scan there are shadows. These are the shadows. These are the regions that aren't contributing whatsoever to the loss, because we just treat those areas as unknown, and there's no prediction being made there at all. So all the brown areas aren't being predicted. They're the same here and here and here. But this large shadow here in the regression network is quite different than in the ground truth, because you see that here, that shadow was caused by this rock that's sitting here. And here there was no rock, and here there is a rock. And so why is that? Because the GAN network knows if I don't put a rock in front of a big shadow, the discriminator is going to know this is fake. The discriminator is going to figure out that shadows need to have rocks in front of them. So it had to put a rock there. Whereas this network is just trying to minimize the average error per pixel. So the rock is small, it doesn't contribute much to the average error. It could just, it may be more beneficial to just, smooth it out and make smoothness be the big criteria. That's what this one is sort of doing. It learned to do, smoothness makes it less overall error in the average. So slightly different answers. They both produce good answers, but they're different in this way, qualitatively different. So, okay, so that was work we did sort of in the beginning, in the first year of the project, and we've got that, all that I showed so far was published in journals, which you could have seen on the bottom of the slides. And now here is what we followed that up with. So in order to get that result that I just showed you better, well, what we noticed was that as you moved further away from the nadir, the nadir being this part right here, so I mean this is directly below the vehicle, the so-called nadir line here, and as you move further away from that nadir, you get worse and worse bathymetry estimates using these neural networks. The error will increase, not surprisingly, as you get further away. And that's because we're not really pinning it in any way. It gets sort of pinned at the nadir, because, we know how far below the vehicle this is, right? But over here, we don't really know the angle. The angle could be drifting up or down somewhat. So in order to fix that, we used, like I mentioned already, the altimeter readings that we have. So here's the altimeter reading that corresponds to that nadir line. We know this altimeter, we could record that, and we make this second image. So we input this image and this image. And here along this line, we have the numbers that correspond to the altimeter readings along the path. But we also have other lines of the survey, and they had also their altimeter readings, and we can actually calculate where they should fall in this image. And we do that, and then we put them in. And then we get some kind of an estimate of the uncertainty. And then we get both an estimate of the depth and then an estimate of the uncertainty. So why do we estimate the uncertainty now? We didn't do that before. I'll get to that. But you can see here that the uncertainty along these lines is lower. You can barely make them out, but you can see that all those lines have lower uncertainty, and that's what we were trying to get at here. And then we have a predicted depth coming out of the neural network. And here, of course, is the ground truth bathymetry, so you can compare that. The reason we calculate the uncertainty is that we're going to now use all of the estimates. For example, right here at this spot here, we're seeing this spot in this side scan image here to the left, But we also obviously saw it when we came on this line, and we saw it from this line, and we maybe saw it from this line, and maybe from that line as well. So we have many views of this spot. So we're going to fuse those views together, and then see and try to get a better estimate. Because the more measurements you have of something, obviously the noise goes down. And in order to do that, we want to have the uncertainty so we know how to weight that average. We want a weighted average, weight it with by the uncertainty. And so that turned out to be a powerful way of doing this. And just a slide here, which I'm not going to talk much about, but maybe if you want to ask me about, you can see some information about the data, about the survey. You see that we had when we did the survey, we knew what we were trying to do, trying to get lots of overlaps, and we've went over the area in many different ways. This is the loss function that you can estimate the uncertainty with. Another thing to notice is that on data set 2, we tested here, this is in the fresh water, this is the salt water, like I said. Here we were training in salt, and then here's another completely different place where we tested it. So we did testing on places that weren't the training place at all, completely different place, with a similar sensor setup. Here's just an image to give you also an idea of like the input. The input is these two images here, the Sparse Steps and the waterfall images, which we don't input the entire image at once. We break it into little bytes so that the neural network can actually work with it, because you can't input too much into a neural network. It gets computationally difficult. And then you get sort of, from that you get, for example, an uncertainty. Here you can see more clearly these lines here where the uncertainty is low because of the Sparse Steps. So this is the output of the neural network here, showing the uncertainty estimate. And you can also see here how the Sparse Step can help us, because here we sort of corrupted these depths, and we sort of added noise to them. And you can see if you add noise to them, this is the output of the neural network, that it's qualitatively like the ground truth. It goes, up sort of, and then down, and sort of come back up again a little bit. So sort of following this pattern of the ground truth, but it's got an offset on it because, well, the Sparse Steps are wrong. So if you get better Sparse Steps, you're going to get a big reduction in your error. So they really do help getting the Sparse Step, not surprisingly, right? And then you could say, how much of these Sparse Steps do you need? Because you saw in that image I had, we had crisscrossed the area a lot, and we got lots and lots of Sparse Steps. And you might think, well, yeah, if you put that much Sparse Steps, and you're practically doing a multibeam survey already. So we removed a lot of them, and as you can see, it really doesn't need a lot of that Sparse Steps. You could take away an awful lot of it. The big jump is here when you go from no Sparse Steps to some Sparse Steps. Then you get a big improvement. Then adding more continues to help, but maybe not so much as you would think. And you can see also that, like, we're down, I mean, pretty low average anyway, errors. I mean, this is, of course, average, mean absolute error, right? So less than a decimeter here on average, but of course we have some big errors in there, so I can't necessarily say that is here you can see actual errors. So here is the ground truth. Up here in the top right is the ground truth multibeam. What we're doing, showing here, is we're showing that if we just sort of average without using the uncertainty, we just sort of equal weight to everything, we get kind of a lousy looking image here, estimate of it from the neural network. So the uncertainty does help, because it produces this image on the bottom here with fewer of these strange artifacts in it, because we've thrown away some really uncertain data, or maybe not threw away, but down-weighted it so much that it doesn't affect things as much. So that estimating uncertainty did help, and fusing the data, of course, helps a lot. And then here you can see the actual errors. So like I said, I mean, okay, the average error is super small, like you saw on the previous slide, because of these big areas here with blue, but then there are some areas here that are getting up in the reds, and you can see here 1.2 meters error there in those areas. So there is, that'll give you a good idea of what it's able to do. Okay, now we have to sort of like get ready for the next level of this, which is so that previous work there, that was Yuping, and now Nils has sort of in parallel with Yuping really worked on a sort of completely different approach to doing this, and then we'll see combining the two together afterwards. But in this approach of Nils, it's inspired from like with camera images, they do things called shape from shading, which is basically you look at the way the light, reflects off of objects, and then if you have some assumptions about where the light is coming from, you can deduce the shape of the object by the way the light is changing as it sort of reflects off different parts of the object. And really the idea there is to sort of make a guess at what the geometry is, and then predict what the image would look like using physics, and then you compare that to what you actually have for an image, and then you try to adjust your geometry to get a better match between it. And that's sort of what we try to do here, except we're doing it with sonar. So the interesting thing, or one of the interesting things that, and this has been done before. I mean, this has been done in 1990s. I mean, but it was done in a much more limited way, I could say. I mean, so what Nils has done is considerably more sophisticated than that, and we're using a lot more data. But the idea is you start with a neural network that is going to be your map. I mean, the neural network itself, it's going to encode the map of this region. You have a region that you surveyed, and now you have a neural network that's going to be that region's map, if you can think of it. So it's like a machine. You give it the neural network an input. This is the X and Y coordinate, and out pops the depth at that coordinate. So you get, and then for some reason on this figure, I mean, Nils called it theta. I mean, that's the depth, okay? So that's the map. I mean, and so, okay, that's a strange way of representing the map. You would think something like, well, why don't you just have like a grid, with heights on it? But no, it's going to be a neural network, and it's going to be like a machine to produce depths, okay? And it's going to be important that we can take the derivatives of those thetas with respect to these X and Ys, and that you can do with a neural network, so that's good, and then we use that. Basically, you're going to use that to produce the theta for, you have your side scan, and then you're going to say, okay, well, here's a whole bunch of, here's a side scan, and you can use this. It's a little tedious, but you can use this to predict. Use this machine to predict what that side scan should have looked like, essentially. That's what we're going to do here. We're going to use the machine to predict a side scan that corresponds to an actual side scan that we have, So we do that, and and in order to do that, you have to use some physical models and assume Lebesgue, for example, reflection and some other things in order to do that. But all that is built into the framework. So you give me a side scan, and the thing generates basically a model using this neural network, what it thinks the side scan should look like. And then we could take the difference in those two, the real side scan here, and this is the one produced from this strange neural network map thing. And we can also input the sparse steps. We still have those sparse steps, so we can have them at those points that we have sparse steps. We can also calculate a so-called loss to propagate back, or an error to propagate back from them. So these kind of losses get propagated back for a particular side scan ping. I mean, we take one ping, and then we propagate an error back. Then we take the next ping. We do over the whole survey. And slowly but surely, this network starts to go from something where we initialize it completely random here. This is the ground truth of the bathymetry there, and this is how this is the neural network, and initially how it's producing a map that looks like this, and this is the normals to the bathymetry. So we look at the normals because we can see a lot more detail there. Plus, they turn out to be really important when you're making these predictions of sidescan. And you can see how over the epochs we slowly approach the ground truth. And so, I mean, in the beginning, you can see it's getting pretty quickly the basic features here. But as you get down here, as you see down here, we're starting to get some of these more distinct rocks here. Not all of them. There's a lot more rocks here than we're getting, but we start to get rocks towards the end. And you know, so you could wonder if we could refine this and find even more rocks. I mean, but at any rate, it's kind of encouraging to see the way it does learn to learn the bathymetry. And so if you can understand now, we sort of automatically take the entire survey, all the lines, whether they overlap or not, they all get calculated in this relatively complicated step that's happening up here, which I kind of glossed over, but there's like ray tracing and strange to find this intercept points and everything else going on there. That's rather complicated, but you know, due to that, we're going to actually correctly calculate a sort of consistent picture of the bottom. And you can also again look at how the sparse steps affect this. So I mean, here we used all the sparse steps, and you can see what the region looked like. There was a lot of lines going through this region, and then we said, well, okay, well, let's just use, I think, I'm not sure how many there are here, a few of the sparse, or a few of the lines for the, and then, yeah, that didn't actually, if you look, it's hard to see here, but it doesn't, not much difference in these two. Here, we just went along the border, the idea being, well, let's pin this. It's sort of like a differential equation. You need to have the boundary conditions. I mean, you need to sort of, have you ever solved, like, it did physics and you're solving, you know, the Gauss law or something, and then you have to define or Maxwell's equation, you have to define the boundary conditions, you know, otherwise you can't solve it. That's sort of what we're doing here. Okay, along the edges, we're gonna need to have it pinned down, otherwise this thing will drift like crazy. And yeah, okay, this is not nearly as accurate as this one, but it's sort of getting some of this, you know, some of these ripples here, you can start to see them forming, and some of the rocks are gone, of course, and some other things. And yeah, so you can also get numerical results. They basically confirm what I just said, that, you know, it gets better the more sparse data you have, but it's actually okay even, well, I mean, here you can see even yeah, this is actually showing that the sidescan is even helping too, because it's not only showing for different amounts of sparse data, but also with and without sidescan. So you might think to yourself, well, wait a minute, if you put that much sparse depths in there, then you could just sort of interpolate between them and you can probably get a pretty decent map. This is showing that that's not exactly true. I mean, that the sidescan is actually, this is the error in the gradients, or this is the error in the bathymetry, the easiest one to understand. So here's like one error, or 1 meter error in the bathymetry here, and this is without sidescan. But if you use the sidescan, you can cut that down, even in the case of just those borders, you know, down to less than 4 decimeters. And if you're using all the altimeters, all the data, it's still a pretty good you know, reduction here in your error. It is true, of course, if you use all those lines, it is partially true that you can just sort of interpolate between them and get a pretty good estimate here. But yeah, I mean, you get even better if you use the sidescan. That's what this is showing. So the next step was that we had all these physical models again. And remember, in the beginning, I talked about how we want to try to see if it's better to use data to estimate the physics than to try to put in to try to estimate the parameters. For example, I mean, you know, what is the albedo the so-called reflectivity, if you will, of the seafloor. I mean, we have models for it. Niels built a model for it, and tried to estimate the parameters of the model. You have the Lambashian reflections. You have the beam, even the transducer beam, which of course we can model pretty well. But who knows? I mean, that might be wrong on the actual transducer that we have, because we'll use the manufacturer's information on that, and maybe that's not actually accurate for the one that we have. So all these things might be better if we just replace them with data-driven models. So that was the idea next, and we said, well, we are already good at estimating bathymetry from sidescan using neural networks. Let's use that same kind of neural network training to learn the normals, because the normals are the things that generate the side scan. That's what that Niels's strange map had to produce. It had to produce the normals, and from the normals you could deduce how the side scan would look. So we could have a neural network learn to produce normals from side scan, and then we could just have an error that looks like the difference in normals, and optimize that in Niels's framework. So Yuping went ahead and ran his stuff again with slight changes to estimate these normals, or what we're calling the gradients here. And then you can just compute the loss and see how that works. And so this is unpublished. I mean, this Yuping is getting close to submitting this now, but we're still sort of work in progress very much. So I'm going to show you some of the results that he has now, preliminary results. And you can see here, there's going to be a series of slides that are going to look like this, but I'm going to swap out things as I gradually get finally to what Yuping did, because what we have here is something that's illustrating the degradation in the model from different effects. So here on the left, we have the ground truth. That's from the multibeam data. That's what you get. You get bathymetry here on the top and the normals here on the bottom, right? So that's what we're trying to get. That's our goal. And then what I have here to the right is still using the multibeam, but we're using the multibeam in a slightly different way. What we're doing is we're using the multibeam to calculate those normals that we would normally calculate with Yuping's special network from the side scan. So instead of using the side scan data to calculate the normals and then trying to optimize things, we're taking the actual true normals and we're trying to make it look like the true normals, from the multibeam. So you might think, well, that should give you I mean, there shouldn't be any loss almost at all if you did that. These two should be identical. But it's subtly not the same thing, because when you take the normal, you have to understand that the normal that affects the side scan image is not the full 3D normal of the seafloor. It's the normal that's projected in the plane of the side scan. The side scan is sort of scanning perpendicular to the direction of motion in a plane. And it's in that plane that the normal matters. So one direction of the normal is going to be sort of removed, and then we're going to use that to train it with. So if you can imagine that you don't really get any information about some places they're normal because you didn't see it from the right angles. You have to sort of see it from two different angles in order to get the full normal, if you will. And so that sort of reduces the amount of information coming in here. And that's what we're trying to show here, that some information is already lost just because of that effect. And in this image here on the right, we used more than the lines you see here. We used 55 lines. There's more. It gets to be a mess, but you saw the image before with lots of lines on it. So we used 55 lines to calculate the gradients, and we got this. And so there's some degradation. And then you can say, well, what if we only use 12 lines, which is what you see here? Then this is with 55 lines, and this is with 12 lines doing that. So you can see gradually we start to lose. I guess this rock isn't as distinct. I don't know. There's not much degradation to go from 55 to 12. That's reassuring. But we're going to use 12 when we go to the side scan. So we want to compare really how much do we lose when we go to the side scan. That's the key. That's what we wanted to find out. And so Now we're using the side scan here, and we're comparing that to that previous 12-line ground truth thing here. So this is maybe we could show the ground truth here, and then you could compare it to that. But this is sort of, in some ways, a fairer comparison of how the neural network is doing. Because I mean, you can't expect the neural network to produce an image better than this, when this one was produced using the true normals themselves. So you can see it's pretty good. I mean, it's encouraging again. We've been getting some of these little rocks here and so forth. Not perfect. I mean, you can definitely, we can study this and see things that are wrong. And then finally, you might want to wonder, well, what about Nils's method? So now this is really preliminary because we're not really sure. This is Nils's method over here. With the physical model in it, and yeah, it's pretty comparable to this actually, and we really have to study it very closely, and we're not even sure this is, we might be able to get this better and so forth. So it's kind of not clear if we've improved things using neural network. I would say that's not what Yuping says, but that's what I say anyway. I'm not entirely convinced he's shown it yet, but at least it's not worse at any rate. And then you can zoom in here to see specific things. So here is, here's zoomed into a place. This is, again, the multi-beam data zooming in to see, okay, well, here we can see individual boulders here. These are pretty big things, but you can see the dimensions here, hundreds of meters here. These are pretty big boulders on the bottom. And you can see how they look in the side scan. This is what we're going to use to try to find those boulders. These are side scans that, some parts of these are this region. I don't know exactly where, but, that I just asked them to put those there so you get some idea. And then you can see, okay, here is the mesh, and here's, like I said, using the mesh again, the multi-beam again, to calculate the normals, but only using 12 lines and like I said, projecting into the plane normal. So not that much degradation. We lost these rocks out here. You can see, oh, this rock is not so good anymore. You can look at individual rocks here and see some rocks have disappeared. And then you can look here, and obviously even more rocks have disappeared. Although, this one seems to be coming back again. But it's good. But it's good. I would just say this is pretty good. Not perfect. It's sort of believably degraded, I'd say. If it was exactly this, I would be like, okay, this looks like maybe we did something wrong here because it shouldn't be perfect. So I think this is encouraging. It's showing that we can find some rocks, and maybe if we keep working, we can refine this even further. Here's just another of the same. Basically the same. Here's another area, So and here's what that area looks like. It's kind of the same story. So the conclusions. It's looking like we could use the neural networks. At least in some cases, these GAN networks in particular are pretty nice for modeling the sonar. In the ways I said, the limitations. Never mind. The point is that we're able to show all of these, exploit those three things I said on the first slide. I think is a way to summarize it, and we're getting some progress. So thank you very much.